these redox reactions in photosynthesis. So we'll go through the overall photosynthesis reaction, the light-dependent part of photosynthesis, as well as the light-independent photosynthesis redox reactions. So the way I go at these problems is to first look at the oxidation states of the atoms in the equation given to you. So in this one, if we look at CO2, the oxidation state of oxygen is almost always 2- when it's paired with a different atom. So in this case, it's paired with carbon. So in order for this molecule to be balanced as far as oxidation states, the carbon must have a 4+ oxidation state. And then you move along to the next atoms. You have hydrogen here, which is almost always a 1+, unless it's paired with a metal ion. So if it's paired with like iron, then hydrogen is actually 1-, but we don't have to worry about that. And then you have these reactions. So if hydrogen's 1+ and there's 2 of them, that must mean oxygen is 2-. Okay, so now we go on the other side of the equation, the product side. So we have oxygen over here, molecular oxygen, and it's paired with itself. So any atom paired to itself is going to have oxidation state of 0. Okay, and now we look at this molecule, and we have hydrogen. It's not paired with a metal, so it's going to have oxidation of 1+, and then oxygen almost always has 2-, 2 hydrogens, 2+, oxygen 2-. These are balanced, so that must mean carbon has 0 oxidation state. So once you have all the oxidation states labeled on your atoms in your equation, then you can begin to figure out what's being reduced, what's being oxidized. So in order to figure out what is being reduced and what's being oxidized, you use the saying, Leo the lion says Ger. So loss of electrons oxidized, and then Ger, gain electron reduced. So if you're going from, if we take a look at carbon here, if carbon is going from a 4+ to a 0, that must mean it is gaining electrons. So we can put carbon dioxide on this side of the equation. And we're going to be using an N of 6. So N is basically the number of molecules that would be used. And if there's a 2N, then you would just multiply 2 times N to get 12. And we'll worry about that later. So we have carbon dioxide on this side because the carbon is being reduced. So you can put the C6H12O6 on the other side, the product side. And now we have, in order to balance this, their charges are already balanced. You just take the whole molecule this would have an oxidation state of 0 overall. This would have an oxidation of 0 overall, so you don't have to worry about the charge. But we do have to balance the amount of hydrogens on this side, so as well as the number of oxygens on this side. This side has 12 oxygens. There's only 6 oxygens here, so if you want to add oxygens, you have to add water. So we add 6 water over here. So now we have 6 carbon, 24 hydrogens, and 12 oxygens. So now we add the hydrogens on this side to balance the atoms, and you add the electrons as well to balance the charges. So we're good up here. All right, so what's being oxidized in the original equation? Oxidized means loss of electrons. So we have hydrogen is staying at 1. Oxygen is actually being oxidized in this scenario because this water is actually the first step in photosystem 2, in which it gets broken down into molecular oxygen. So, and you could also see that this oxygen is going to be split into molecular oxygen. This oxygen stays with the carbon atom here in order to make the glucose. So we have the oxygen going from 2 minus to 0. So we can add in 12 water goes to 6 molecular oxygen. That's a no. And now, so we have 12 oxygen on this side, 12 oxygen on this side, but we don't have 24 hydrogens. You add to 20. And the charges on both these are 0, so you don't have to worry about that. So add in your 24 hydrogens, and both sides are balanced. And now in order to get your net equation at the end, you cancel out what is like on opposite sides of the redox. So here we have 12 water, 6 water, so this gets reduced to 6. 24 hydrogens here, 24 hydrogens there, cancel those out. 24 electrons here, 24 electrons there, cancel that out. And you're left with 6 CO2 plus 6 H2O goes to 6 O2 here glucose molecule. And that is your final balanced equation. And you can see from the initial equation that this was already balanced as far as charges, but you did have twice as, or 4 times as many, or yeah, twice as many hydrogens on this side than you did this side. If you were to put in 6 here, you would have 24 hydrogens and only 12 hydrogens on this side. So we ended up balancing the hydrogens going through this redox. Okay, so now let's look at the light-dependent reaction. So the photosystem 2 or photosystem 2 and 1 reactions happening in the chloroplast. So once again, we look at the charges of the atoms and molecules, and we look at the oxidation states. So once again, we have water, and we know that, oops, let's get that. We know that hydrogen has +1, and oxygen has 2 minus. And here we already know what the oxidation state of NADP is, because NADP plus just signifies +1. And then we look on this side, liquid oxygen has 0 oxidation state. And then here we know hydrogen is a 1 plus, so that must be an NADPH, it's a 1 minus. So what's being reduced here? We have, so basically what's gaining electrons, or what's gaining hydrogens is another way of looking at it. And NADP plus goes from oxidation state of 1 plus to 1 minus, so that must mean it's gained electrons. And you can see here it gained hydrogen, so we can put that in the reduction portion of this reaction. It is being reduced. And if you think about what's happening during photosynthesis, NADP plus is being reduced from the ferredoxin NADP plus reductase enzyme. So that makes sense, at least biologically. Actually, let me put in the numbers. So this would actually be 12 NADP plus and 12 NADPH, or no, 6, since we're using N of 3 in this scenario. So 6 NADP plus and 6 NADPH. Okay. So in order to balance this, you can already tell this is not balanced either with the amount of atoms or the charges. We have a 6 plus charge over here. We have neutral charge over here. So what I'm going to do is just add 6 hydrogens over here. And these hydrogens are actually coming from the proton gradient being made during the light-dependent overall reaction. And those hydrogens are being pumped across the stroma, or pumped from the stroma into the thylakoid lumen during this reaction. So we have the charges equal now. So in order to balance this as far as atoms, we can see we have 6 hydrogens here, 6 hydrogens here, and we need to add 12 hydrogens total over here with the 12 electrons. So now we are balanced as far as charge and atoms. Okay. So it's being oxidized once again. We have water. It's being split in molecular oxygen. So we can put in 6H2O, and we saw this on the previous overall reaction. We balance it similarly. We add 12 hydrogen on this side and 12 electrons. These charges, oxidation state of this is 0, oxidation state of water is 0. So we're balanced charge and atom. So now we start canceling to get our net equation. We cancel out, these 12 hydrogens here, 12 hydrogens and electrons here, and then that's about it. We don't have to cancel anything else. So write in our final net E balanced equation, 6 NADP plus 6 water goes to 3 oxygen plus 6 NADPH plus 6 hydrogens. Okay. So lastly, let's look at the light independent reaction. So here we have a lot of stuff going on. We have CO2 and NADPH and water going to CH2O, which if you have 6 of these, you end up with the glucose and then your NADP plus. So this is basically restoring the electron carrying capacity of NADP and making glucose. So you could think of this as just the second half of overall photosynthesis. And first, we're going to start out like before, figuring out the oxidation states of these atoms and molecules so that we know what's being reduced and oxidized. So oxygen has a 2- when it's paired with something other than itself. Carbon has 4+. To make this balanced, we saw NADPH before. Hydrogen has a 1+, so that must mean NADP plus. NADP has a 1-. Hydrogen here has a 1+. Oxygen has 2-. Okay, and we saw this in the overall reaction. Hydrogen has 1+, when it's not paired with a metal ion. We have oxygen 2-, this is balanced. Carbon has 0, and now NADP plus is 1+. Okay, so one thing that could be confusing is that what's happening here with the water? Well, you can just completely ignore the water because it is not being used in the redox steps of the light independent reaction. This water is actually being used to turn ribulose 1,5-bisphosphate into 3-glyceraldehyde phosphate. So this water is just being used as far as those first enzymatic steps to create 3-glyceraldehyde phosphate. So you don't have to worry about this. And what you do need to worry about is carbon, because you can tell this is being reduced. Your oxidation state is decreasing. So let's put in 6 CO2. Goes to C6H12O6. 1 molecule of glucose. And we can balance this first, similarly as we did before. The charges are already the same, so we just have to add in the 6 water over here to balance the amount of oxygen. So that must mean we add 6 times 2 plus 12 hydrogens, 24 hydrogens here, and we balance the amount of atoms. And then next, what's being oxidized? NADPH is being oxidized to NADP plus. NADP's oxidation state is increasing, so that must mean it's losing electrons. It's going from -1 to +1. So let's put 6 NADPH goes to 6 NADP plus. Okay. All right, let's look at this. You can already tell that your charges are off, so let's add 6 hydrogens here. Your charges are balanced, but we have to add in 12 hydrogens here to balance the amount of hydrogen atoms. Okay, so 6 hydrogens in NADPH, 6 hydrogens here, 12 hydrogens, okay. And we have +6 here, we have +6 here, okay. So now in order to get our net equation, we start canceling like terms. There's 12 hydrogens, 12 electrons. There's no I messed up here. It's supposed to be 12 NADPH and 12 NADP. That is why our hydrogens and electrons aren't canceling. So we just go back real quick. 12 NADPH, 12 NADP plus, and 12 hydrogens here to balance the charge. 12 hydrogens. And this should be 24 hydrogens and 24 electrons in order to balance the electrons and hydrogen, or yeah, in order to balance the hydrogens on this side, since there's 24 hydrogens. Okay, all right, that makes sense. All right, so 6 CO2 plus 12 NADPH plus 12 hydrogens goes to, and you're just taking the net of the redox step because you're getting the net redox reaction, not the net full. So you would not add in the waters up here. So it goes to C6H12, O6 plus 6H2O plus your 12 NADP. So this should be balanced with the charges. There's 12 hydrogens here, 12 NADP plus here, 12 NADP, 12 NADP, 12 hydrogens, 24 hydrogens, 12, 12, 24 hydrogens, 6 carbon, and 6 oxygen here, 6 oxygen here, 12 oxygen here. So we're good. All right, thank you for going through these redox equations with me. And if you have any questions, just email me and I'll get back to you.